Hey, everybody. View reader mode. There we go. Someone gonna hack me through PowerPoint? What the hell is that? How much of Linux is just a command line flex versus actually better than Windows OS? Um, I would say that it's a lot easier to develop code in Linux, just because it has all the compilers and stuff like that, and it's really easy to kind of compile your own code, and so I think it's a lot better in terms of that, because Windows is not really designed for developers. It's more more for end users, which is kind of that's why you kind of see it mostly used by most people. But I do find that developing code is a lot easier than Linux than Windows. I mean, if you want to get into like code development work, I would say I would recommend it. But so if that's something that you see in your future and it's a skill that you want to work on, I would say go for it. Oh, I see. Yeah, it's becoming it is becoming more of a in-demand skill, especially because a lot of tools are going digital nowadays, and so just to have some kind of basic programming and basic Linux skills, I think would be useful. We're going to go over that stuff in 417 though, and so in 417, we're going to go over basic Linux stuff, and so I'd say after 417 you can add it to your resume. Oh, definitely. Yeah. Deep learning, machine learning, all that stuff is super trendy right now. And I think it's, yeah, a lot of people are going in that direction. Oh yeah, definitely. There's a lot of open source deep learning softwares in Linux. I know Google has a big one called TensorFlow, or at least that was kind of the big name when I was in grad school. I haven't checked up on it in a while, but yeah, absolutely. There's a lot of oh, nice. But yeah, there's more options available for you in Linux, and I think it's a lot easier to kind of modify things in Linux as well. Yeah, because in order to run code in Linux, all you really need is just a text editor, and you just need a text editor and the terminal. But in order to run code in Windows, like you have to have a special kind of program to run it. And so just developing code and running code just a lot easier in Linux. Yeah, and so that includes open source machine learning, deep learning stuff as well. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Good, Professor. How are you doing?
Good, I'm good. That's good. All right. So yeah, it's 2 more weeks to go, week 15, and so I know it's been a long semester, but we're almost at the end of it. Right? Okay, and so this week is going to be a tale of 2 different class sessions. So I think today will be relatively chill, and I think actually we'll end pretty early today because I don't think this is going to take us the whole time. And then Thursday is going to be the midterm. So yes, first question. So is this going to be on the midterm? No, it's not. And so today we're going over a new set of lecture slides called Flow Phantoms. And so this will not be on the midterm. And so the last lecture that's going to be on the midterm was covered last Thursday, which is on microcirculation stuff. Okay. And so that's the last thing. Today's lecture will not be on the midterm. Okay. And you'll see kind of why, because this is kind of a very different set of lecture notes that compared to the ones before. But yeah, so the last thing that you need to do was last Thursday. And again, the midterm is going to be all conceptual questions, right? And so there's 8 conceptual questions, and so there's no problem solving. And so if you understand the concepts from the last few weeks, you'll be good to go. Okay. And if you had a chance already, I've already posted the review for the midterm, and so that's on YouTube, that's on Canvas, right? And so the way I structured that review session was just to go over the learning objectives. Right. And so if you do that, you go through the study guide, you nail all the learning objectives, you're going to be in great shape for the midterm. Okay. All right. And so besides that, yes, eight questions, but they're all conceptual, and so they're all just type it in the browser. Yeah, conceptual questions will be like the last midterm, and so yeah, just same kind of same style of questions. And so last midterm, I think we had 5. We had 5 conceptual questions and 1 problem solving, the LPM question. And so I basically took the time that it took me to do the LPM question, and then I just shifted those into conceptual ones. Yeah. Yeah, there's a lot of concepts we've gone over since the midterm, and so there's a lot I could have asked you on it. So yeah, it's be good. Okay. Okay, and so that's going to be our next class session this week. And then next week we have the final week. And so I do have something exciting to announce for next week. And so I was able to secure a guest lecturer for next Tuesday. And so, I've kind of been talking to him all semester, but finally we decided on something after I bribed him with food. And so I have to buy him dinner in order for him to do this. But he did agree to come. And so he's a good friend of mine. So his name is Adam Updergrove, and he works in industry right now. And so he works for a company called HeartFlow. And they're a really exciting new company. And so they're a bioengineering company that they rely on simulations like this to do their work, right? And so they're kind of one of a kind in the industry right now, because I think a lot of the bigger biotech companies, they're kind of dabbling in simulations a little bit, and they're kind of exploring the space. But HeartFlow is all simulation stuff, and so they use simulations to do a lot of really cool things. And so I would definitely and I'll send an announcement too, because these lectures become less and less populated as the semester goes on. But I want to make sure that everyone knows about the guest speaker on Tuesday. Okay, and so bring your questions too, because he brings a really nice perspective that I can't bring, and that's a perspective from industry. Okay, and so I kind of jumped right into this job right after grad school. And so I don't really know, I've heard stories, of course, but I don't really know exactly what it's like to be out there in industry doing this kind of work. And so, I think for a lot of you, I think a lot of you guys have goals to work in industry, either doing this kind of work or something related to this. And so, definitely come with your questions, because Adam's a great guy and he's always happy to answer those kinds of questions. Okay. So definitely look forward to that next Tuesday, right? And I think it'll be kind of a nice cool down session after the midterm as well. Okay. All right. And so so besides that, it's a little bit late right now to assign any more homework. And so I've decided I'm not going to assign you any more homework for the rest of the semester. And so the only two graded pieces of work that you need to worry about for this class will be the midterm on Thursday, and of course your final project. Okay. And I have noticed that most of you have turned in your final project geometries either on Canvas or I got either your Dropbox or Google Drive links. And so I haven't had a chance to look at those yet, but I plan on starting those probably sometime tomorrow. And so you can expect some feedback over the next couple of days on your final project geometries. Okay. Okay. So I think that's all the announcements. So are there any questions before we get started today? Okay. All right. And so let's go ahead and jump into the lecture notes. And so again, I think this is a fairly short one, and so I think we'll end kind of early, but it's also quite different. And so I think in a lot of ways this might be pretty exciting for a lot of you. And so this is a topic called flow phantoms. Okay. And so in this class, we're going to talk about what flow phantoms are, what they're used for, and some materials that are used to construct them. Okay. All right. And so the first question to ask is, what are flow phantoms, right? And so flow phantoms are basically testing devices that you see on the right. Okay, and so this is very different compared to what we've done in the class, because everything else we've done about this class, we've been discussing blood flow in terms of mathematical, or computational, or conceptual models, right? And so there's been one aspect that's been kind of criminally missing throughout this whole class, and that's the experimental side or the physical side. Okay. And because, you can do all the calculations that you want. You can do all the modeling, you can do all the computations, supercomputers, some vascular, all that stuff. But all that is meaningless without any kind of real world validation, okay? And I say that, as a very strongly computational guy myself. And so, if you've been out in industry and you kind of know that, the engineering community is in more ways than one, but one way that is fragmented is, you're either a computational or analytical guy, or you're an experimental guy. Okay. And so, based on the work that I do, I'm very much in the computational theoretical side. So I do everything, in computer stuff like that. And I don't really work on with real data. Okay. And so there's always a debate of, which one's, better than the other one, which one's more important, yada, yada, yada. But as someone that's very strongly in team computational, I will tell you that, computational stuff would be nowhere without real life measurements. Okay. There's just no way around it, because, in reality, we live in the real world, right? And so until Elon can get his brain links, star bullshit thing together, we're going to live in the real world, right? And so in a lot of sense, all the stuff that you do in the computer won't really matter unless it's actually validated. And so experimental science, experimental engineering will always have a strong place in science, okay? And what we're going to go over in today's lecture are some of the different methods that you can use, that's used out there to do kind of experimental studies in blood flow, right? Have I seen Elon with the mullet? No. So I actively try not to follow Elon as much as possible, because I think his ego is just out of control. But I know a lot of the stuff that he works on. Yeah. Okay. And so I don't think I need to introduce you guys, what experimental fluid dynamics are, because I think everyone kind of has been exposed to it in one way or the other. And so I want to really focus on what are the aspects that make experimental cardiovascular fluid mechanics difficult. Okay. And in particular, one of the most challenging aspects of this is just recreating the same kind of conditions that you would get inside the body. Okay. And this goes on many different levels. And so the first level, that we'll talk about a lot is just the geometry, right? And so you guys all know that, you're using Simvascular, that the geometries that you're working with in the cardiovascular system are very strange, very complex, right? And so you can see that on the right? And so you can see that this is a heart model. And so you can see that it's a very weird geometry, right? It's not just a pipe. And so it's a lot of weird bendy pipes, right? And so not only that, you have to get the properties of the fluid correct, right? And so the blood has to be all good. And for a lot of cases, you might want to get the material properties of the wall correct too, okay? And so when people say the general term flow phantoms, it's kind of a blanket term. It's kind of a general term to refer to any kind of experimental device or setup used to mimic cardiovascular flow, okay? And so, mostly we'll talk about, construction of the geometry, but there's going to be a lot of other factors as well, okay? And I'll say that, this kind of work is really important because I visited Edwards Life Science down in Irvine, and they have a ton of these in their testing facility, right? And so they have a ton of these flow phantoms that test flow in these realistic cardiovascular geometries. And so, a lot of this knowledge will be good to know. And unfortunately, I'm not an expert in this stuff by any stretch of the imagination, and so, we're only going to go over just the basics. But, what I'm hoping for in these lecture slides is to introduce you to these basics, and then, so that you can kind of use that and kind of get used to kind of the terminology and get used to kind of the general methods, so that you kind of take that to the next step. And, and if you're interested in pursuing this. Yeah. All right. Okay. So any questions on this so far? Oh yeah. 3D printed soft tissue is a whole nother ballgame too. So yeah, that's getting pretty close. Compared to where still relatively pretty far from being put inside real people on a regular basis. But considering where it started from and where it is now, it's come a really, really long way. It's fascinating. Yeah. Okay, and so let's go ahead and continue on. Okay. And so the question is now is why do we want to use flow phantoms? Okay. And so, and in particular, the comparison that I want to make is what I call in vivo measurements, right? And so in vivo measurements, what that means is taking measurements inside a real person, right? And so why would you go through the trouble of creating these kind of sophisticated experimental setups when kind of the best geometry and the best conditions are inside every single person anyway, right? And so why don't we just measure stuff inside real people and then we'll call it a day. And so there's a lot of reasons why you would do this. And so the first reason is control, right? And so if you have a setup in your laboratory, you can control the flow conditions and the geometry, basically, to the little dots on your eyes, right? And so that exact amount of control, you need that in order to perform any kind of systematic study, right? And so you don't get that in a real person because you can't put someone on a bike and just crack the whip and say make sure you get 80 milliliters of flow in your cardiovascular system. It just doesn't work like that. And so in order to get specific flow conditions and certain pressures, you need to have some kind of experimental setup. Okay. Right. And so the second reason you would do it is reproducibility, right? And so this is the hallmark for any kind of experimental study. And so you want to make sure that your measurements and your analysis is repeatable. Okay. If you have a very controlled experimental setup, you can do that very easily. Okay. Next is licensing and safety. Okay. And so, the obvious thing is, for an experimental setup, no one has to sacrifice their body for science, which is, usually a good thing. First, because as much as we say that, no one actually wants to do it, right? It's a little bit hard to find someone that said, please cut me open and measure me for the sake of science. And, most people won't be okay with that. And the last reason, which is kind of the cool part, is just optical transparency, right? And so you can construct these flow phantoms to look kind of like this, where you can actually look inside the flows and actually see what's going on. And that's super cool, right? And so, you can actually see the flow patterns developing, instead of relying on some kind of, imaging framework, okay? All right. And so the main disadvantage to using flow phantoms is that it can be a little bit difficult to manufacture the exact geometry or to find the exact materials. But, as with any science, the techniques are kind of advancing every single day. And so this becomes less and less of an issue as techniques get more and more improved. Okay. All right. Oops. Okay. And so the question now is, what are flow phantoms used for? All right. And so the first usage for flow phantoms is to investigate a flow field, right? And so you can use the fact that your flow phantoms are transparent, or you can also include some other kind of optical imaging systems, some like high-powered cameras, maybe some lasers, to measure the flow and to view it, very precisely. Okay. And so you won't be able to get that, inside a person. Okay. And that first part is key too for its connection with computations. Okay. Because if you can imagine, if you're running your three-dimensional computational fluid dynamics CFD, right, the way that you validate it and the way that you prove that your simulation is legit is one way you can do it is you can compare it to like flow phantom measurements, right? And that a lot of that's been done in the literature quite a bit. Okay. All right. And so actually that gets into the second point. And so the second point is, validation of flow field data, either from simulations, which is what I just talked about, or from imaging. Okay. Because, if you kind of remember from our past lecture notes on medical imaging, there's a lot of techniques out there that can be used to measure flow. So things like phase contrast MRI, PCR MRI, or Doppler ultrasound, right? And so in order to make sure that these measurement techniques are getting accurate results, or maybe to better develop these techniques, you can compare them to flow phantom data that you get from a lab. Okay. And so the last usage for flow phantoms, which we'll talk about near the end of the lecture today, is to investigate the relationship between flow and biological function. Okay. And so one really cool usage for flow phantoms is that you can actually put real human cells inside these experimental setups. And you can see how those cells react to certain types of flow conditions, right? And so this is how, a lot of the studies on like mechanotransduction have been performed in the past, right? And so a lot of those studies were performed by taking, real human endothelial cells, putting them inside a flow phantom, running an experiment and seeing how they actually react to the flow, okay? Okay. And so these are kind of all the different uses for flow phantoms. And typically, as with most experiments, the research question or the thing that you want to find out, the thing that you want to find is that's formulated first before you build your flow phantom, right? Because it's not often that you build a flow phantom and then you say, what can we answer with this? A lot of times you're trying to answer a very specific research question or a very specific kind of validation question, and then you construct your flow phantom to specifically address those questions or address those goals. Okay. And so that's usually how these things work. And so you come up with the question first, you come up with the research issue, then you construct your experimental setup, you construct your flow phantom, specifically designed around that goal in mind. Okay, so any questions on this so far? Okay. All right, so let's go ahead and continue on. All right, and so let's start with flow visualization phantoms. Okay, so this is probably the most common type of flow phantom, and it's the one I have most of the pretty pictures for because they just look really cool. Okay, and so what you're seeing on the right here is at first it looks like an X-ray, and so this looks like someone's knee joint or something like that, but it's actually a flow phantom. So you can actually see kind of the outline of this flow phantom, and if you can imagine, it's made of plastic and see-through, right? And what you're visualizing here in these lines, these are the patterns of the fluid flow, right? And so the blood is coming in and it's going around this kind of, I'm guessing this is some kind of disease or something like that, and it's coming out the top, right? And then on the right figure right here, the flow has been disturbed a little bit. And so maybe this was a bubble and it popped, and you see the flow kind of going into that space, right? And so this is the power of flow phantoms, because you can get really detailed, really pretty pictures of the flow field inside these geometries that would otherwise be impossible, okay? And so, the way that these flow phantoms work is that they have to be made of some kind of optically transparent material, okay? Because it has to be designed so that scientists could actually look into these flow phantoms and take really nice pictures, right? Because as you can imagine, these pictures here were captured using a very high-powered camera, okay? All right. And so, in addition to that, a lot of the flows inside these flow phantoms, they're usually seeded with some kind of particles or some kind of material or some kind of dye that can be easily picked up by cameras, right? But if you do that, you have to be very careful, because any particle or any kind of material that you put inside the flow, it has to be called what's called buoyantly neutral, okay? And so what that means is that it has to have a density that's very similar to the flowing fluid, which is in this case blood, okay? Because what you don't want to happen is you don't want to have particles that are either heavier than the fluid or more dense, or less dense in the fluid, because you don't want the particles to kind of drift due to buoyancy, right? So you don't want them to either go up if they're too light, or you don't want them to sink if they're too dense, right? So they should be able to just kind of suspend, kind of perfectly inside the fluid, right? And so they shouldn't all fall down to the bottom, and they shouldn't all go up to the top, right? And so you have to be very careful about the particles and the materials that you put into these flow phantoms. Okay. All right, and so probably the most common way to visualize flow in these flow phantoms is to use a technique called particle image velocimetry, or the term you'll hear a lot in industries called PIV. Okay, and so this is probably the most common and probably the cheapest way to perform flow visualization. Okay, and so under this technique, usually what you're going to do is you're going to put a bunch of particles in the flow, usually at a pretty low density, so usually less than 1% of the volume. And this is mostly just not to affect the flow, okay? And then what you do from here is that you use a pulse laser sheet to visualize the particles in a single plane, okay? And then what you can do from there is you can use a high resolution video camera to record, the particles as they pass through this laser, okay? And so by observing how much the particles move in between frames of the camera, because you can imagine the camera is capturing things at 60 frames per second, 120 frames per second, by measuring how much the fluid particles change position, right? And with this, it's very easy to see that, this particle moved this much in between the frames. From there, you're able to infer things like the velocity field or the vorticity, okay? And since, I just did kind of a terrible job explaining that, I do have a video here that kind of explains how this is. So actually, I need to share my laptop audio. So actually, let me go ahead and share my screen one more time. Okay, and let me know if you guys can't hear sound, but I did just enable it, so let's go ahead and watch this video.
Okay, so today I'm going to show you how we experimentally visualize airflows and get numbers on airflows. And the way that I normally do that is known as particle image velocimetry, or PIV. It's a fundamentally simple technique at heart, but it's quite complex in reality. So I'm going to show you through some of the basics and talk you through the experimental facility here. So, basics of PIV. To start with, you have a wind tunnel. I've lopped off the front of the wind tunnel in this diagram for clarity, and just indicated where the flow is coming into the tunnel with the flow arrow. The center bit is the test section, which is where you put the stuff in that you want to look at, and then the back is the sort of exit diffuser or expansion that goes into the tunnel fan. It's this relatively small bit, the test section, that's what we're interested in. Now, because I've got a long diffuser expansion section on my tunnel, I've actually put a camera in that section there. Now, why I've got a camera here will become clear later. Up the top, there comes a laser sheet down that's held by a laser probe that's on a traverse. The traverse allows the sheet to move forwards and backwards. This allows me to look at different sections of the airflow as it goes along. For a more three-dimensional representation of this setup, we can see here the laser attached to the traverse holder at the top and the camera shooting at the back. Now, the point where the camera looks at where the laser is illuminating is the bit that we're actually looking at and trying to investigate. But why do we want random images of a laser sheet? Well, simply put, we seed the room with a lot of particles. Kind of, you can imagine like a sort of smoke, but it fills the whole room and is quite a consistent density. And this laser is actually fired in pairs. So we get multiple pairs of images at really close spacing. We're talking sort of 50 microseconds or less, so very, very tiny time spacings. So when we get these two images here, we get them received at the camera, and between the two images, the flow has moved somewhat in the tunnel. So we look at those two images, we see what the difference is between the two, and from that we can see how much the flow has changed. Now, we can see stuff actually because we have images of the particles, and we can see the particles because the laser at very high intensity is shooting those particles, and the light is scattering off those particles and being reflected back to the camera. So for this testing today, we've got two vanes, the laser probe.
All right. And so, from there on, you can view the rest of the video if you want from the lecture slides, but that's kind of just the section that I wanted to talk about. All right. So Isaac, your question are the phantoms flexible to any extent, or are they rigid? They're mostly rigid. And so you can design phantoms that are flexible, but the ones that most of that we'll see are kind of like the ones that we saw kind of at the very beginning, where you have kind of the pipes that are inset into like this kind of this kind of resin block basically. And so these are pretty rigid, and so you have to kind of make it of a different material if you want to have flexible flow phantoms. Yeah, great question though. All right, and so that's PIV, and so very, very cool technique. Relatively inexpensive. And it's used by a lot of places. And so if you ever get the chance to try one out or to see one in person, I would definitely take it. And call me too, because I haven't actually had a chance to see one in person either. And so I'd love to go see one someday too. But any study that's that does any kind of experimental fluid mechanics. And so here obviously you see kind of the probably most likely in aerospace or some kind of environmental application, because they're talking about air. But you can use PIV for like blood or water or anything like that as well, right? And so it's a very flexible, very reliable technique that's used quite often. Oops.
Okay, so today.
Okay, we're done with you, British boy. Right. Oh, you tried this in AirWeb. Oh, nice. Yeah, yeah. Call me next time. I'd like to see it one time too. Yeah. Okay. And so let's talk about phantom construction. And so just like we talked about, in order for you to see the flow inside of phantom, it has to be made of some kind of optically transparent material, right? And so some common materials for this include glass, acrylic, polyester, or silicon. Okay. Because the geometries that we're usually working with inside these, for the cardiovascular system are pretty complex. One of the more common methods to do these, and I would say this is kind of it's getting to be a little bit of an old school method because 3D printing is becoming a huge thing now, is to use a casting operation. Okay, and so we'll talk about that in kind of an example on the next page. Okay, but since 3D printing is becoming much more popular and much better, what's becoming much more common is for scientists to just simply 3D print something like this or like this, and that'll give them the geometry that they want, in a very, very simple kind of way. All right, and so let's talk about an example for how these kind of used to be done in the past, right? Believe it, actually, this actually does rely on a little bit of 3D printing, but this is kind of like old school 3D printing before it came to be good. Okay. All right, and so the first step in this process can be shown here in step A, right? And so in step A, the first thing you have to do is you have to create a CAD model or some kind of computer model of your vessels of interest. Okay, and so you can use a software. You can use Vascular for this, or you can use any other CAD software. Right, and so like something like SolidWorks would work as well. So as long as you can get a computer representation of the geometry, then you can get that. Okay. And then from that CAD model, what you then have to do is you have to 3D print a mold. Okay, and so a mold is something that you can kind of open up, and that that you can basically has a hollowed out cavity where that vessel is going to be. Okay, and so usually usually this mold is usually printed in two pieces, and so you print kind of one side of the mold first, and then the other side, and then you kind of put them together like this. Okay, and then inside that mold, what you do is you pour some kind of metal that's usually a very low melting point in order to form a core, right? And so a core is usually something that you see like in figure B right here, okay? And so this is made of some metal that's a pretty low melting point, right? And so that's going to be key for the next step, okay? Because then what's done from here is that this core is put into some kind of box, right? And this box is designed so that it has inlets and outlets for the flow to come in and out, okay? And these inlets and outlets also come probably with some screws so that you can screw in some pipes and or hoses or some other stuff in there. Okay. And then from there, some kind of polymer, or in this case, a liquid silicon elastomer is poured over the mold. Okay. And then from there, it's allowed to kind of set. Okay. And so from there, you have kind of this box around it. And then from there, what you do is you heat it up. And so you heat it up to a temperature that's higher than the melting point of this metal, but lower than the melting point of this elastomer. And then what you do from there is that the metal is going to melt, and then you just simply pour it out, and then you get a flow phantom that you see here in figure C. Okay. So you can see, it's a fairly involved process, and it's it's becoming less and less common because nowadays people just 3D print this whole thing, and that's usually good enough. But kind of the benefits for this is that because you kind of start with a mold. After you get this kind of metal part right here, you can kind of sand it down a little bit, right? Because what can happen sometimes with fully 3D printed parts is that you kind of lose a little bit of resolution because the 3D printer only has so much resolution. But if you create a mold like this, what you can do with the mold is that you can kind of smooth it out or kind of adjust it a little bit to kind of account for those kind of irregularities or imperfections. Okay. But 3D printing is getting better and better. So, there's more and more people that's just, saying, let's just 3D print this whole thing. And, maybe we can sand it out later on. Okay. So any questions on this? Okay. All right. And so that's, phantom construction. Okay. And so now let's talk about phantoms for medical imaging. Okay. And so just like we kind of talked about at the beginning, another common use for flow phantoms is to test medical imaging technology. Okay. Specifically those that are used to measure flow. So things like Doppler ultrasound and PCMRI. Okay. And so if you plan on using some kind of medical imaging together with flow phantom, they have to be constructed a little bit differently than normal. Okay. And that's because you have to choose a material that's compatible with the medical imaging technique. Okay. And so, in these cases, because you plan on, putting an ultrasound probe on these, or maybe putting it in an MRI machine, whatever material that you use for the flow phantom has to have kind of the same properties, as tissue and blood. Okay. It doesn't have to have everything exactly the same. It just has to have enough so that the medical imaging technique can't tell the difference between them. Right. And so, just for an example, let's consider ultrasound. Right. And so if you're constructing a flow phantom to test ultrasound techniques, then you have to make sure that the material that you construct the phantom from has the same kind of sound quality. So basically sound travels at the same speed and scatters in the same way through the phantom as it would through human tissue. Okay. And so, that can mean different things for different type of techniques. And of course, with MRI, you want to make sure that your material has the same, electromagnetic properties as tissue. Okay. And so in these kind of situations where you plan on using the phantom for medical imaging, the medical imaging device or the medical imaging technique, that's going to drive your that's going to drive your phantom design. Okay. And so one obvious example of this is that you don't want to use any metal parts around an MRI machine unless you want to die and to send your part flying, because you're putting a piece of metal inside a giant magnet, and you're basically asking for trouble. Okay. And so with that, we have to think about what types of materials that are out there that can mimic tissue and vessel properties exactly. Okay. All right. And so let's start with some off-the-shelf material properties. And so a lot of off-the-shelf material properties will work with MRI. And so things like acrylic, things like glass, things like PTFE, things like latex, right? And so these materials have relatively little effect on the measurement of velocity via MRI. And so MRI is actually, not that difficult to work with in terms of finding materials, right? And so of course the only requirement is that they not be made out of metal. And so I actually had a colleague in grad school who did experiments inside an MRI machine, and she used a lot of these materials. And so they're just very common materials that you can find in any kind of fluid mechanics lab. As long as they're not metal, then usually good to go. Okay. And so acrylic is actually a great material to use for CT. And so since they have the very similar X-ray attenuation characteristics as tissue, right? And so if you're testing CT stuff, acrylic is a great property for that. Okay. But if you have some type of solid material like polyester, these often don't work with MRI because they don't return an MR signal at all. And so if you try to use something like polyester inside an MRI machine, it's going to lead to some unrealistic looking images. Okay. And that covers most of kind of the common materials that you can find, either in a hardware store or off the shelf, right? But what's common too is that, in order to mimic, very specific tissue properties, or to, mimic them better, scientists often make their own properties, or they make their own materials. And so a very popular material that scientists use to kind of construct their own phantoms from is agar. And so agar is really nice because it has a lot of similar acoustic and MRI properties. Okay. And so this table down here kind of shows you, kind of the differences in between tissue and tissue with agar, right? And so you can see that, a lot of these properties, and so these are MRI properties. And so, these T1, T2, these are MRI specific things. If you kind of remember, the details from the medical imaging lecture, this is kind of the time it takes for, the the protons and neutrons to be excited, that's T1, and then T2 is the amount of time it takes to relax. Okay, and so these are their measurements under 1.5 Tesla, which is like a half power MRI machine, or 3 Tesla, which is the full powered MRI machine. Okay. All right. So any questions on this so far? Okay. All right, and so here's some more properties, and so these are acoustic properties of auger, right? And so this basically compares what the speed of sound is inside these materials, as well as this attenuation coefficient, which if I'll be honest, I don't know what the attenuation coefficient is, but it's something that's important for ultrasound, but I don't know enough about ultrasound to really know what that is. But I know what speed of sound is, and so I know what this stuff is, but attenuation coefficient is something I don't know. But you can see here that auger, and you compare that to a lot of other materials here. Auger has very similar properties as ideal tissue, right? And so for ideal tissue, the speed of sound is 1540 meters per second, and for auger you have 1551, which is basically right there, and your attenuation coefficient is 0.52, and your attenuation coefficient for ideal tissue is 0.5. So again, basically right on the money right there. Okay. All right, and so let's talk about blood mimics now, right? And so that's tissue mimics, but you also need to have a fluid that's going to mimic the properties of blood well as well. Okay, and so blood mimic refers to basically the fluid that's run through your phantom, and again, it's important that these have very similar physical, acoustic, and MR properties as the blood. Okay. Most of all, the most important property that that your blood mimic has to have is it has to have similar viscosity. Okay. And so if you can have a viscosity that's around 3 to 4 millipascal second, then you're usually pretty good. MR property stands for like their electromagnetic properties, or how they act in an MRI machine. Yeah. And so you want to make sure, of course, you want to make sure that you don't put any metallic particles inside your fluid, otherwise it's flying in the MR machine. But it should have, this relatively the same number of protons, neutrons, things like that. And when you expose it to a magnetic field, it should react in kind of the same way as blood. Yeah. All right. And so the most common blood mimic that's used in practice is a mixer. And so you use a mixture of water and this fluid called glycerol, right? And so the most common ratio is 40% glycerol and 60% water. Okay. And so this achieves this viscosity really well, and it has really good MR properties as well. Okay, and so this is commonly used, and so this is what you'll read in most of the textbooks. But if you talk to anyone that's done experiments, people hate working with glycerol because it's sticky, it gets everywhere, it's impossible to clean. It's really terrible. And so what you'll see most of the time is that for experimentalists, they'll troubleshoot their experimental setup and they'll get everything set up with just water first, right? Because water is nice because you can just clean it up with a paper towel if it spills, right? And then only when they're absolutely sure that everything works well, that's when they start to add the glycerol to their fluid. Because if you spill glycerol, it's a nightmare. You're gonna spend literally days cleaning that stuff up because it gets everywhere and it's sticky, right? Or at least that's how it's described to me. So I've never tried working with it, but every time it's mentioned, people are like, ugh, glycerol. It's one of those things. Right? And so that works great if you're just concerned about the viscosity and you're just concerned with the MR properties. But if you want to work with the fluid that's going to mimic the ultrasound properties, you need to actually embed your fluid with some kind of particles, right? And so usually what's done is that researchers will embed these nylon particles that are about 5 micrometers in diameter. And so these basically simulate kind of the same size as blood cells, right? And so the blood cells actually play a big role in scattering your ultrasound waves. And so in order to practically mimic that, you need to seed your fluid with particles as well in order to get that same effect. Okay. All right. And so how are these phantoms constructed? The ones for medical imaging, right? And so even though these use different materials and different bloods and different blood mimics, their construction methods are relatively the same. And so you can use, you can either, if you can use 3D printing, that's great. But I think what's more common is the casting approach that we talked about, right? And so you make a mold and you make a cast and you use that in some kind of box, okay? And that's especially true for agar, okay? And this table right here, this is one that's shown in one of the textbooks. And so this gives you, some of their, a lot of their properties and a lot of the common materials, okay? Okay, so any questions on this? Okay. All right, and so for the last 2 slides today, let's talk about biological flow phantoms, right? And so these are a very special class of flow phantoms. They're technically not phantoms because they're not in kind of the geometry that we know, but they're used for studying biological flows, and so we classify them as flow phantoms, right? And so these are special kind of phantoms that incorporate real biological tissue to study their response from fluid mechanics, right? And so we use these to study the effects of pressure, the effects of velocity, wall shear stress on real human cells, right? And so these are the kinds of setups that are used to study like mechanotransduction, okay? And so as you can imagine, this extra dimension of adding these cells and culturing them and making sure that they don't die, this adds a huge layer of complexity and difficulty to a typical flow phantom, right? And so in order to make sure that, that you actually get your results from this, typically these biological flow phantoms use very, very simple geometries, right? And so the geometry, one example of that is shown here on the right, okay? And you're literally, instead of, flowing blood through, something that looks like this, which is a realistic geometry, what you're doing instead is you're flowing blood through, just a really tiny channel, basically, right? And because, what has to be done is, usually people, they grow these cells in some kind of, test strip or some kind of test, test flat thing, right? And so basically after they culture the cells, they just put the flow channel just right on top, okay? And so you're gonna see a lot of geometries that are kind of rectangular in shape like this, okay? And so, and so to read this kind of diagram right here, what you have in the middle, this is where the flow actually goes. And so the flow is actually going to come in from one side here. It's going to flow over all the cells, which is on this like hexagon thing. And it's going to flow out here. And then that's going to be sandwiched in between these two, these two plates right here. Okay? One of them has the cells. Okay? And then this entire contraption, this is usually put on top of a microscope because the microscope is needed in order to study, the behaviors of cells, because the cells are, really, really small. And so in order to see, how they're reacting and their behavior, you have to have some kind of microscope in order to study their behavior. Okay. All right. And so, there's a lot of variations in different setups for these biological flow phantoms, but a lot of them contain these essential components. Okay. Excuse me. Right. And so the first component is the endothelial plate, right? And so what this plate is, this is responsible for housing all the cells and keeping them alive, right? And so, on the endothelial plate, we have these endothelial cells, excuse me, and these are usually cultured, by the scientists somewhere separate from the experiment before the experiment, right? And this is usually done on some kind of material called, like glass, and that's usually done for rigidity, okay? And since it usually takes time for the cells to culture and grow, because they need to culture and grow, they also need to stick to the plate, right? You don't want to put this plate into the flow and then flow fluid over it, and the cells just kind of go with the flow, right? And so they need to stick to the plate, okay? And so sometimes, depending on the type of experiment, depending on the amount of flow, the scientist might put some additional surface coatings on this plate in order to make sure that the cells kind of stick to it. All right, and so that's the endothelial plate. And so opposite of this plate, we have the opposite plate, right? And so this plate is mostly just to make sure that that everything kind of stays in place, right? And so it's there mostly for sealing purposes to make sure no fluid gets out, right? And it's often made of some kind of optically transparent material so that you can go in with you can put a microscope right on top of it and really kind of examine what's going on. Okay. All right, and so the next component is the flow chamber geometry, right? And so this is kind of the middle part that you see here, right? And so this determines the flow patterns that's going on top of the endothelial cells, okay? And so usually this is chosen to be some kind of, relatively simple geometry, because what this really relies on is it relies on the scientists kind of, really understanding, what the flow conditions look like, right? And so this is a little bit different than the PIV setups that we saw before. And so, we're not going to have a high-powered camera. We're not going to have a laser sheet going through this flow. And so in order to estimate things like the velocity, in order to estimate things like the wall shear stress and the pressure, the scientists have to be able to predict this using things like either a simulation or maybe just hand calculations, right? And so in order to simplify that process, usually the flow chamber geometry is chosen to be pretty simple, right? And so probably the most complex thing that you would see in these kind of flow chambers that you might have some kind of turn, or you might have some kind of bifurcation, right? If it's relevant for the study, okay? But it's usually not going to get any. It's usually not going to get any more complex than that, because again, these studies depend on the scientists being able to say, I'm running this experiment and I know exactly what the wall shear stress is on these cells without having to measure. Okay. All right, and so that's the flow chamber geometry. And so the next characteristic is the pump. Okay. And so just like any kind of flow, you need some kind of pump to force it through. Okay. And so that's the goal of the pump. Okay. And so you can either do steady or you can do pulsar flow, depending on the type of experiment that you want to run. Okay. The next component is the fluid. Okay. And so the fluid, has to be some kind of blood mimic. And so, ideally it should mimic the same viscosity of blood. All right. But it should also contain the same kind of osmotic or ion concentrations of fluid in the body, okay? Especially if you're studying the effects on cells, right? And then the last component is the microscope, right? And so in order to observe kind of the cellular response, in order to view those, you're probably going to need a microscope in order to view those things, okay? And so usually these kinds of setups come with a microscope so that you can view that stuff. Okay, so are there any questions on this? All right. So if there's no questions, that's all I had planned for today. And so like I said, today was probably going to be a pretty chill day. And so yep. So yeah, we'll let you guys off a bit early. And I wish, I wish I had more to talk about on these things, but this really is kind of outside my expertise. And so, I'm just going off based on what's in the textbook and, what's in what I've heard from colleagues of mine. So, definitely, this really only scratches the surface on this stuff. And so if you're really interested in looking at this more, I would, think of this as more of a starting point more than kind of a comprehensive thing. And so, especially if you're interested in working for like Edwards Life Science, they do a lot of work that's concerned with flow phantoms. And so, I would definitely ask around there to learn more. Right? Okay. And so, so that's all I got planned for today. So thank you guys for tuning in. Thursday is our midterm. And so remember about that. Okay. And so if you want to come in on Thursday, I'll be here, but if you'd rather take the exam in peace, that's fine as well. Right. And so if you're coming on Thursday, I'll see you then. But if not, I'll see you next Tuesday for the guest lecture from my friend, Adam. Okay. Any tips for the test? And so I would look at the study guide because the study guide contains all the conceptual learning objectives. And I would go through those and make sure you can answer all of those. And so I'll tell you, the way I developed this test was I had the learning objectives open on one side of my screen, and I was reading those. And I said, what questions can I ask that's not exactly the same as the learning objectives, but all within the same area. Okay? And so if you can answer all those learning objectives, you're golden for the test. Yeah. All right, and so I'll see you guys on Thursday. So have a great evening, everyone.